Unit 3, Homework 8 is kind of a big departure from everything we've been looking at with exponential, logarithmic, and inverse functions. What we're going to be looking at now are solving systems of two linear equations. So we're back to working with lines. When we talk about a system of linear equations, we're talking about two equations on the same set of axes. So we have three situations that could occur. We could have two equations that never touch. These are called parallel lines. Parallel lines have the same slope, don't forget. And here we have zero solutions or no solution to the system. The system is these two equations. And if we have no solution, this is called an inconsistent system. So that's one situation that we could have. Another situation that we could have is I could graph my two lines, and my two lines intersect at a particular point. So we could say that this is the point, let's say 1, 2. So this has a single solution, and this is the usual typical case that you'll see is a single solution. Now if this was inconsistent, this is called a consistent system. That means a solution exists. Now our next case would be where if I graph one line, the other line runs right into it, and they actually end up being the same line. So these have the same slope, but they have a different, or the same y-intercept as well, whereas these have different y-intercepts. So these parallel lines have the same slope. The same lines have the same slope here as well. However, this one, because they cross at all points, have an infinite number of solutions. Now this is called a consistent system as well, because it has a solution. And in fact, it has an infinite number of solutions. I guess we already wrote that up here, so we don't have to write it again. Infinite number of solutions. It's also called a dependent system. It's called dependent because one line runs into the other. They're the same line, basically. So graphically, that's what this looks like when we're trying to solve. We have parallel lines in two of the cases, but one case they have the same y-intercept, so let's make note of that. Now if we were to extend the red line, it would overlap right over the green, whereas over here we have different y-intercepts. So visually this is what we're up to today. Now there's different ways that I can solve linear systems. There's three methods that we'll look at. The first one is graphically, just like we've done up above before. The second method is called substitution. And the third method is called elimination. And a lot of times in your homework set it'll say use substitution or use elimination. But the truth of the matter is you just need to look at it and decide which method you think works best for you. And then based on that method, go ahead and solve the problem. So let's go ahead and start this by working lots of problems. So for this one, let's not start with solving quite yet. Let's check to see if we have some solutions to some systems first. So let's determine if the ordered pair 1, negative 2 is a solution to the system. And the system will be y equal 4x minus 6 and 3x plus 2y equals negative 1. Well, if it's a solution to a system, Basically what that means is no matter which one I plug the 1, negative 2 in, it's going to come out as a true statement for either one. So it's really important that we kind of keep that in mind. What it means is it doesn't work for one, it has to work for both of the equations that are provided. So a solution to a system will work or be true for both equations in the system. Okay, so let's go ahead and check y equal 4x minus 6 first. Let's check this at 1, negative 2. Okay, so y would be a negative 2. The equal I don't know about if that's true or not. X is 1 minus 6. So negative 2 equals 4 minus 6. Negative 2 equals negative 2. So far, so good. Now I can't just check it in the one, I have to check it in the other as well. So now I have 3x plus 2y equals negative 1. And I'm checking this at the ordered pair 1, negative 2. So I have 3x, x is 1, plus 2y. Y is going to be equal to a negative 2 equals negative 1. And again, there's a question mark up here because I don't know if this is true. 3 times 1 is 3. 2 times negative 2 is negative 4. Negative 1 equals negative 1. So this is true for both equations in the system. So therefore, 1, negative 2 is a solution to the system. Now again, you have to make sure you plug in those values for both equations in the system. Let's look at another one. Let's determine if the ordered pair 2, negative 7 is a solution to the system. And the system that we want to consider here then would be 5x plus 2y equals negative 4, or 2x minus 3y equal 27. So we need to plug 2, negative 7 in, and it must work for both. So I have to work with both. Okay, so let's go ahead and get started with the 5x plus 2y equals negative 4. That's 2, negative 7. So again, I'm plugging in a 2 for my x, a negative 7 for my y, and I'm checking to see, does this equal negative 4? So 10 minus 14 negative 4 equals negative 4, so this checks. But I have to check both. So now let's check 2x minus 3y equals 27. So x is 2, y is negative 7, and I want to know, does this equal 27? Negative 3 times a negative 1 is a positive 21. 21 plus 4 is 25. 25 does not equal 27. Therefore, 2, negative 7 is not a solution to the system because it didn't work for both of them. It has to work for both of the linear equations, just not one. So 2, negative 7 is not a solution to that system. Now, graphing is not going to be an easy method to solve systems of equations because you always have to solve for y, and sometimes that's not very easy to do. But with some of these, I'm going to show you a couple different methods. I'll show you graphing as well, and then you can choose which method you think is easiest based on what you're given or provided in a problem. So let's go ahead and solve the system. And the system I want to solve is going to be 2x minus 2y equals 9. And then I have y equal 2x minus 5. Now a couple things here. This one is really nicely set up for substitution because I have a y equal. That means I can plug this into this one up here. It's really not set up for elimination. So this would be a really good one to use substitution with. And the reason I choose that is because I already have this set up and I have a y equals stuff. So let's go ahead and start this one with substitution. Now when I'm using substitution or elimination, sometimes I can get some strange answers. Let's say like 12 equal 14 when I get done. There's no variables involved. That's a false statement. That means I have an inconsistent system. If I work through with substitution or elimination and I get a true statement with no variables, let's say like 2 equal 2, that's called a consistent system, but it's a consistent dependent system where I have infinite number of solutions. So I'll write that out if we come to that case. So what I do is I want to substitute y equal 2x minus 5, because it's already solved for y, because you have to solve for a single variable, into 2x minus 2y equal 9. So this value of y, what I'll do is plug in 2x minus 5. So it's going to look like 2x minus 2. And then in place of the y, I'll have 2x minus 5 equals 9. So I'll distribute through the minus 2, so I'll have a minus 4x plus 10 equal 9. 2x minus 4x is a negative 2x plus 10 equals 9. Subtract 10 from both sides. Get negative 2x equals negative 1. Divide both sides through by negative 2. I get x equal 1/2. Okay, so now I know my x value. How do I find my y value? You find the y value by plugging in x equal 1/2 into either equation. I can plug it into either equation. I should get the same answer back. I'm going to just plug it into the y equal 2x minus 5 because it's already set up for y equal. So in place of x, I'll put a 1/2. Half of 2 is 1. The 2's cancel here, so I get y equal 1 minus 5, or y equal negative 4. So that means, therefore, 1/2 negative 4 is a solution to the system. And I found that one with substitution. Now let's go ahead and do another problem, and let's use elimination. Now, actually I should probably double check these. So let's go ahead and check. I remember my system was 2x minus 2y equal 9. And I want to check what's going on here. 1/2 negative 4. So I have 2 times 1/2 minus 2 times negative 4. And I'm wondering, does that equal 9? Half of 2 is 1. Negative 2 times negative 4 is a positive 8. 1 plus 8 equals 9. So that checks. But I have to check it in both of them. My other equation is y equal 2x minus 5. And we want to check that at 1/2 negative 4. So negative 4 equals 2 times 1/2 minus 5. Half of 2 is 1. 1 minus 5 is negative 4, so it checks. So you can always plug these in and check these answers. Okay, let's go ahead and look at a problem where we're using substitution. Now some problems, like I said, wait, we just did a substitution. Let's do elimination. Some problems, like I said, are better set up to solve one particular method over the other. So when we solve by elimination, what we're looking for are signs that change. They go positive, negative, or negative, positive, or some easy way for me to eliminate one of the variables. And it usually doesn't matter which variable I eliminate. We just want to make sure that we eliminate one. So let's go ahead and solve the system. And when we solve the system, x plus 5y equals 21, and 4x plus 3y equals negative 1, I can see right away there's nothing solved for x equal, y equal. I could solve this for x equal up here pretty easy, but for this one, let's go ahead and use elimination. Now what we do with elimination is we manipulate one or both of the equations till we get to a point where we can solve. So for instance, at the top here, if this had been a negative 4x, negative 4x plus 4 would have eliminated. So I think that's going to be my strategy. So my strategy is to multiply both sides by negative 4. So that means multiplying not only both sides, but all terms by negative 4. So what we have on the top then is negative 4x minus 20y equals negative 4 times 21 is a negative 84. Now the most common thing to do is to forget to multiply this middle term, because sometimes we just think it's whatever's on the left and whatever's on the right, but it has to be all terms to keep that balance. Underneath we have 4x plus 3y equals negative 1. Oh, okay, so I forgot to write the 4 down right here. So the 4 was originally up here, I just forgot to copy it down. Now when we add these together, these cancel, and I'm left with negative 20y plus 3y is a negative 17y equals negative 84 minus 1 is a negative 85. To solve, I divide both sides through by negative 17, and I would end up with y is equal to 5. Now that's not my complete answer. I need to also find x. To find x, plug y equal 5 back into either equation. Now it doesn't matter which one. They should both yield the same value of x if this is the correct value of y. So let's see what our options were up here. X plus 5y equal 21. I think I'll do that one. So x plus 5y equal equal positive 21. So I'm going to plug a 5 in here. And I get x plus 25 equal 21. Subtract 21 from both sides, 25 from both sides, sorry. X equal negative 4. So these are my two values. Therefore, I have the ordered pair negative 4, 5 is a solution to the system. In fact, in this case, it is the solution to the system. So I should replace that. It's the solution. There's only one. If there was more than one, I would have come up with an infinite number of possibilities. And I'll show you an example of what happens when we do that. So it's the solution to the system. And remember, we can check it. So we would go ahead and take x plus 5y equals 21. And I would check this at the ordered pair negative 4, 5. So negative 4 plus 5 times 5 equals 21. Negative 4 plus 25 equals 21. 21 equals 21. Check. And then I have 4x plus 3y equals negative 1. And we're checking this at negative 4, 5. So I have 4 times negative 4 plus 3 times 5 equals negative 1. Negative 16 plus 15. Negative 1 equals negative 1. So this checks. So I'm confident that this is my correct solution. So that's how you solve systems of equations. Now, not all of them are going to be that straightforward. For instance, sometimes you might have, something that looks a little bit different. I might have fractions involved, or I might need to solve or move everything across to one side before it works. But you can definitely solve using any of these methods. But usually when you look at a problem, once you set it up, you're going to say, oh, I can really easily use elimination, or I can really easily use substitution. Let's go ahead and look at an example where we're using graphing. So let's go ahead and solve this system. X minus 2y equals negative 6, and y equal negative 4x plus 12. Now if you're going to use elimination, you need to make sure all the x's and y's are on the left and constants are on the right. Now this one looks like, to me, it's better set up to use substitution. Just pop that y back in there. But I want to use graphing. Now to use graphing, I have to set both, not really set both, I should be careful how I write that. I should say solve both equations for y equal. So this one's ready. Y equal negative 4x plus 12. This one I need to still solve. So for this one, I have x minus 2y equals negative 6. I'd subtract the x from both sides. Negative 2y is equal to negative x minus 6. And then I divide both sides through by negative 2. And when I say both sides, I really mean all terms. Negative divided by negative is a positive 1/2 x. Negative divided by negative is a positive 3. So y equal 1/2 x plus 3. So this is what I'm going to graph. So let's open up a calculator. And when we're graphing, we're going to use 2 lines in my equation editor. Okay, so I'm graphing both of these, so I'm going to choose y equal. So I got my y equal, so my first one is y equal 1/2 x plus 3. So 1/2 x, whoops, 1/2, I just scoop this up a little bit, x plus 3. Okay, now my second equation was negative 4x plus 12. Negative 4x plus 12. So I'm going to graph them both. One should be blue and I think the other one should be red. And we're going to see where they cross. Okay, so they're crossing at this point right here. So it looks like my x value is 2 and my y value is 4. But let's go ahead and go to second table. See what's going on there. So we thought it was 2, 4. But what we're looking for my y values to be the same. Oh, here it is right here. So here's 2, and then each of the y values is 4. So that means that they are matching up or agreeing on that being the solution. So let's go ahead and snip this. Actually, let's go back a step. What if it wasn't so obvious what the solution was? I could find that by going to second calc. And what we want to do is scroll down here to the 5th option on my calculator called intersect. So our first question is, what is the first curve? And that's my blue one. So I hit enter. And then the second curve, what you want to do is just move your cursor to your second curve. And I think it seems like it's stuck on my... Okay, so it is on here. So if you look at the top, see it's in red, the negative 4x plus 12. So I can hit enter. And then I think I'm close to my guess right there anyway. And then I see it says my intersection is at 2, 4. So I had some problems, I guess, moving it around and coming up with skipping curves. But if you look at the top of the screen, it kind of shows you where you're at. So this helps you find that intersection point using that second calc intersection feature. So once I have both of those graphed, wherever they cross is my solution. Now sometimes it's really easy to see where that solution is, and sometimes you'll have to go to the table or the intersect function just to double check what the actual solution is. So this is the ordered pair 2, 4. So this is my solution. This is 2, 4. And I can tell from this information down here. So that's the ordered pair 2, 4. Let's go ahead and pull that table in as well, because the table provides us with some good information there. It's because my solutions are integers that it works so well. If my solutions weren't integers, then I'd probably have a little bit of trouble because decimals are not going to show up on my table unless I set it up to do that. So let's go and snap this bit. So this is how I know that this is my solution, because the y values are the same. That tells me that the y values are the same for that x value of 2, so they agree. So that's an example of solving a system by graphing. But before you can solve a system by graphing, you have to solve for y equal on both. Let's just go ahead and work through some random problems, and we'll decide which method we want to use. Now remember, we're using substitution, elimination, and graphing. Now I think our text uses the addition method for elimination. So elimination or the addition method mean the same thing. One key thing to keep in mind, if it says you have to use substitution, you don't have to. They don't know how you solved it. So use the method that you're best with and that you think makes the most sense for the problem. Okay, so for this problem, I have 5x equal y minus 3, 5x minus y equals 7. I think for this one, I want to think about elimination. But first of all, I want to get everything on both sides of the equation. So I want all my x's and y's on the left, all my constants on the right. So I'm going to go ahead and subtract y from both sides. So I have a new system now. I have 5x minus y equals negative 3 because I subtracted the y over. And I have 5x minus y equals 7. So with that small change, I have a new system of equations. So I think elimination still looks best. This is interesting. The 5's are the same, the negative front sign up front is the same. I wonder if that means anything. So I'm going to use elimination. And again, I think your textbook calls this the addition method. They just mean add the equations together. And it doesn't matter what method your book says to use, you can use any method you want. So I have 5x minus y equals negative 3, 5x minus y equals 7. I'm going to multiply the top through by a negative value. Now the reason I wanted to multiply through by this negative value is so I can get my 5x's to go away. So I'm going to have a negative 5x plus y equals positive 3. Then I have a 5x minus y equals 7. Oh my gosh, everything eliminated on the left, and on the right I'm left with 10. 0 equals 10. 0 does not equal 10. This is a false statement. And because this is a false statement, that means I have an inconsistent system. I have parallel lines. So what this means is no solution. There's not one value of x and y that I can plug into these equations to solve them simultaneously. So for this particular one, because I have that false statement, it means inconsistent. I have parallel lines. There's no solution. So when you get a false statement, that's what you want to be thinking about. Let's go ahead and solve another system. So for this one, let's solve the system x equal 6y plus 5 and 2x minus 12y equals 10. Now, when we're working with these types of setups, it's better usually to have all the x's and y's on one side and constants on the other, but this one is set up really nice for substitution. So again, choose your method. And the reason I think it's set up so nice for substitution because it's solved for x. So I'm going to plug x equals 6y plus 5 into the equation 2x minus 12y equals 10 and solve. Okay, so 2x minus 12y equals 10. Now in place of this x, I'm going to put in 6y plus 5. Now we'll take the 2 and distribute, so I have 12y plus 10 minus 12y equals 10. And then I want to solve for y, but let's look what happens. The 12y minus 12y cancel, and I'm left with 10 equals 10. Okay, this is a true statement. Remember our last one was a false statement. This is a true statement. This means I have a consistent, dependent system. Now I can have a consistent system that only has one solution, but because this one is a dependent system, I have an infinite number of solutions. Basically, these are the same lines. One line runs right over the top of the other line. So a way you could think about this is one line runs right into another line, and they end up having all the same solutions that would solve. So it doesn't matter if you're using substitution or elimination. If you get a true statement, you have a consistent dependent system. If you have a false statement, you have an inconsistent or no solutions. Now there'd be no challenge to solving systems of equations if we didn't throw in one with a fraction. So let's go ahead and throw in this system. So let's go ahead and solve the system. And we'll have x over 3 minus y over 3 equals negative 1, and x plus 2y equals negative 9. Well, when I look at this, I'd rather not work with fractions, so I want to clear the fractions. And after I clear the fractions, I'll choose a method. And I'm going to multiply both sides through by 3, so by multiplying by 3. So when I multiply by 3, every single term, the 3's cancel. So I'm left with x minus y equals negative 3, and x plus 2y equals negative 9. So there's my system. And I think I'll use elimination here. Now, there's a lot of different ways I could do elimination. I'm going to multiply the top equation through by 2, because then I'll get my y's to cancel. I could also multiply through by a negative 1 to get my x's to cancel. It just doesn't matter. So I'm going to multiply my top and my bottom through by 2. Now this 2 distributes, so my new system then is 2x minus 2y equals negative 6, and x plus 2y equals negative 9. The y's eliminated like we wanted. 2x plus x is 3x. 3x is equal to a negative 15. Divide through by 3, and I get x is equal to a negative 5. Now how do I find y? Well, we find y by substituting or plugging in x equal negative 5 into either equation. And in fact, not only either equation, but I have a lot of stuff running around here. I have my original 2, and then I have this other equation that I came up with that I multiplied by 2. But I think it's probably better to go back to the original, and of course I will avoid the fractions at all cost here. So let's go ahead and plug it into x plus 2y equals negative 9. So x is equal to negative 5 plus 2y equals negative 9. I'll add 5 to both sides. I get 2y equals negative 4. Divide by 2, I get y equal negative 2. So my solution is negative 5, x comes first, negative 2. That's my solution. Now you can go ahead and plug in and check as well, like we've been doing before. Another thing you could do is solve for y and try and graph. So we've looked at a lot of solving these systems. We haven't really looked at any application problems for solving linear systems or working with linear systems. So let's go ahead and look at that next. So the first one we're going to look at is a business application where we're learning to write the cost function, and then after we write the cost function, we'll be looking at how to write a revenue function as well with some additional information. So we'll take this step by step and answer each question as it is asked. So first of all, it says write the cost function. They recommend that we use C of x for the cost function. Well, I have two types of costs. I have fixed costs. That means the costs that even if I don't manufacture anything, meaning I have salaries, I have rental for my equipment, I have the lease on the building, those are costs that I have even if I don't purchase or sell anything. Then I have my variable costs. My variable costs basically involve how much it takes to produce each item. And in this case, I have 120 for each canoe. And so they tell me, okay, using x as the variable. So we'll use x here for my variable. So this is my cost function. So this is fixed costs plus variable costs. It's a good lecture question right here. What is my cost function? It's my fixed cost plus my variable costs. So my cost function for this is 24,000 plus 120x. Now once I find the cost function, I can also look at my revenue function, and that's the one number that I didn't use here. So let's go ahead and look at the revenue function next. Now the revenue function basically means how much money do I make when I sell each item. Okay, so revenue function, that's this other number that I haven't used up here. The selling price is $240 per canoe. So my revenue is 240 times X. Now this is not taking into account the cost that it created for me to get this canoe out on the selling floor. It just says how much money do I make? How much money do I bring in? Then I have to subtract out my costs in order to find my profit, but we're not quite to that point. Now X is the number of canoes sold. So if I sold, let's say 10 canoes, I would have a revenue of $2,040. So this is my revenue function. Okay, let's go ahead and see what the next question is. These are multiple questions. It says determine the break-even point. Okay, well the break-even point refers to the point at which I finally start making money, if you want to think about it like that. So let's go ahead and look at determining the break-even point. So the break-even point is when my costs and my revenues are the same. So if we were to look at a graph of what was going on here, we'll assume that we're only selling positive values of X. I might have my cost function. So this would be my C of X. And then I would have my revenue function. This would be my R of X. And at this very point where they intersect and they basically agree that my values are the same for X, my number of canoes I need to produce for a certain profit is my break-even point. And again, like I said, this is a point where we start to make money. Below this, my revenues aren't as high as my costs, so I'm losing money. At this point, they're the same. Above this point, I'm making more money. I'm bringing in more revenue than my costs, so I finally start to make money. Well, to determine the break-even point, you have your cost function, 24,000 plus 120x, equaling your revenue function, 240x. So let's go ahead and solve. I like my variables on the left. You could also solve this by moving the 120 across. So I'm going to move my negative 24,000 over. I have negative 120x equals negative 24,000. I would divide both sides through by a negative 120. And I have x equal, negative divided negative is a positive, and I have 24,000 over 120. And 24,000 over 120, of course we want to reduce that. And we get value here for x equal 200. So 200 canoes. When I sell 200 canoes, I'll finally have made enough money so for the 201st canoe, I will actually make money. I will have covered my costs and can start to make money. Now it asks for, what does this break-even point mean? Well, you know what? First of all, let's back up a little bit. If x is 200, what is y? Well, to find y, I could plug it into this equation for cost or this one for revenue. It doesn't matter. I think I'll plug it into 240x. So this value of y comes from 240 times x, which is 240. We decided x was 200 for our break even. So if I take 240 times 200, my y value is 48,000. So I sell 200 canoes, my cost is 48,000. If I sell 200 canoes, I bring in $48,000. And so I've covered all the costs of doing business. Now we want to know, what does this break-even number mean? So they give us several options to choose from in order to interpret this break-even number. So break-even. This means, let me put the word break-even up here so we remember what we're looking at. This means that when the company produces and sells the break-even number of canoes, which in our case was x equal 200, there's more money coming in than going out. There's less money coming in than going out. The money coming in and going out is equal. Okay, so that's the option that we're looking at here. That's why it's called break even, because they're equal. Okay, this next problem is kind of a departure from our business problem we just had when we were looking at break even. And this is a problem where we're rowing a boat. So take a few minutes to read through it if you'd like, and then we'll go ahead and set it up. A lot of information going on here. It says when a crew rows with the current. So when it's with the current, that means the current is helping you go faster. It travels 22 miles, which is a distance, in 2 hours, which is a time. Against the current, the crew rows 10 miles, which is our distance. So this is against, in 2 hours time. So this is 10. X is equal to the rowing rate in still water. Y is equal to the rate of the current. It says find the rate of rowing in still water and the rate of the current. So we're looking for two different things here. So they have to set up this table, which is really nice. It says rowing with the current. I have our crew's rowing rate plus the rate of the current times the time for 2 hours, and the distance is 22. And then over here, when I'm rowing against the current slows us down, so that's why we have subtraction. And I'm still rowing for 2 hours, but I'm not getting as far. I'm only at 10 here. So to get started, it says find the rate of rowing in still water. Okay, so we have a formula that's noted at the top here that you might not notice. It's distance equals rate times time. So to abbreviate that, a lot of times we say D equals RT. So for our first equation, I would have 22 equals distance, rate is x plus y, and time is 2. So here's my distance equals rate times time. Now for my second equation, I would have my distance is 10, my rate is x minus y, but I'm still having a time of 2. So this is my system of equations. So I need to solve this system. So I have different methods I could use to solve. I have graphing, substitution, and elimination. Before I determine which one I want to use to solve, let's go ahead and rewrite these. So I'd have 2x plus 2y equals 22. So that's 2x plus 2y equals 22. Just flip the directions. And then here I have 2x minus 2y equals 10. Well, these are set up perfectly for elimination. The y's eliminate automatically. And I have 4x equal 32. Divide both sides through by 4. And I get x equal 8. Okay, so now I need to figure out what y is. To find y, plug x equal 8 into either equation. And it doesn't matter which equation we use, we should get the same answer. So I'm going to use 2x plus 2y equals 22. You can use the other one if you want. So 2x plus 2y equals 22. Oh, I was supposed to put in 8 in place of x. Let's plug an 8 in there. So I have 16 plus 2y equals 22. So let's go ahead and subtract 16 from both sides. We get 2y equals 6, divide through by 2, and I get y equal 3. So this is my ordered pair that solves that system. So the rate of rowing in still water is blank miles per hour. How do I know if that's 8 or 3? Well, if we come up here, it says x is the rate in still water. So solving for x down here, that was 8. So once we get that solution, it'll ask us for our next one. So I'll pull in the question so you see exactly what it looks like. So for our next one, we have the rate of the current in miles per hour is the next thing it wants us to solve for, but we've already actually done that because we know the value for y. And that's y. So this is x, and we know that from above. This is y, and we know that from above as well because y is the rate of the current. It gave us that information. So y is equal to 3 here. So again, it's just a matter of going through, making sure you read those directions so you can remember which values are x and y, and then working from there. We're going to work through one more story problem or application problem. Now this one, a little picture might be helpful. So let's go ahead and sketch out a picture right after we read the problem. Okay, the last story problem that we're going to be looking at today, or application problem, a picture will really be helpful. So we're looking at a rectangular lot. So right away we can draw a quick picture of a rectangular lot. They give us the perimeter, and they also tell us that we're fencing 3 sides of the lot. So here's our rectangular lot. We're not fencing the 3rd side, so maybe there's a creek or something over here. And I have dimensions of width, and some sort of a length. So we have a couple of things. First of all, perimeter is P, so we can go ahead and start with P equals 360. If I were to march around this perimeter, and I guess if we use this as a creek, we'd have to march through the creek, it'd be W plus L plus W plus L. So that's 2 times the length plus 2 times the width is equal to 360. Now my cost, let's see, an expensive fence along the lot's length is 35 per foot. So the cost to fence this distance is 35 times L, the number of feet. And then $5 per foot are on the sides. So this is $5 times the number of feet. So I know that 35L then would be the cost of the long side. Each of the smaller sides would be 5W plus 5W or 10W, and the total cost is $4,550. So this is my system of equations. Now in order to make this easier to solve, I'm going to note that all of these are even numbers, so I'm going to divide through by 2 here. So I have length plus width equals 180. And then here I note that all of these are divisible by 5, so I'm going to divide these through by 5. 35 divided by 5 is 7, so I have 7 times the length plus 2 times the width is going to be equal to 4,550 divided by 5, which is 910. So this is my new system of equations. Now let's go ahead and eliminate the w's by multiplying through by a -2 on every term of the top. So we have a -2L minus 2W equals -360. So I guess I started back where I came from here. Just the signs are opposite. And then below I have 7L plus 2W equals 910. The W is eliminated like we wanted. 7L minus 2L is 5L. And 910 minus 360 is 550. Divide both sides through by 5, and I get L equals 110. Now to figure out what W equals, I would just plug that back into anywhere I wanted to up here. So I'm going to say 2 times 110 plus 2 times the width equals 360. So 220 plus 2W equals 360. 2W, 360 minus 220 is 140. So I get W equals 70 here. So these are my 2 dimensions. Now in my math lab, it specifically asks you, what is the longer dimension? You'd put in 110. What is the shorter dimension? You'd put in 70. If you have any questions on the lecture or need any help, please stop by my office, bring your questions to class, and of course the Math Center is always open for you to stop in. Thanks a lot, and good luck on this assignment.